Hello. Welcome to the first lecture in college algebra. In Unit 1, there are 6 subunits. Today I'll be lecturing on the first, sets, and if all goes well, I will be posting lectures for the remaining 6 sections as well. Sets. Okay, we should start at the beginning. What is a set? A set is a collection of objects whose contents can be clearly determined. Right? So we might say all the students currently enrolled in this class would be a set. We can define that as a set because if I were to look at the roster, I would clearly know which students were in this class and which students were not in this class. The objects of the set are referred to as elements. So if you're a student in this class, then you are an element of the set of students in this class. Okay, it's very important that sets are well defined. That's one of the basic things that determines a group as a set. We have to easily look at the definition of that set and know whether something is in that set or is not in that set. All right, we can represent sets different ways. We can represent sets as a word description. An example here says the set of n is a set of whole numbers greater than 0 and less than or equal to 9. Another method to represent sets is the roster method. In the roster method, we identify the name of the set using the same example that we just used in the word description. We'd say the name of that set is n, and that set equals, and we would list out all of the elements that satisfied that word description. So that set would equal 1, 2, 3, 4, 5, 6, 7, 8, and 9, because those are the whole numbers that are greater than 0 and less than or equal to 9. All right, a third method for representing a set is set builder notation. In set builder notation, we say the name of the set, we use the equal sign to show what that set is equal to, and then we define an element that we define a variable that represents all the elements in that set. So this same set, these whole numbers greater than 0 and less than 9, could be written in set builder notation as the set of all x, and that vertical line reads such that the set of all x is the variable that we've chosen to represent the element, the set of all x such that x is an integer greater than 0 and less than or equal to 9. All right, one important set when we are studying set theory is the universal set. The universal set defines all the elements that we might be analyzing. All right, so, and one example of a universal set would be the students enrolled in this class right now. Okay, we could then analyze those students. We could say I'm interested in just the students that wear glasses, or I'm interested in just the students that identify female. Another example, more mathematical in nature, would be in roster method, the whole numbers, including 0, up until 9. Okay? A couple of examples of the universal set. A subset is a set of the universal set, or it could be a subset of another set that contains all of the elements that are in the universal set, or the other set that it's a subset of. Right? We have a symbol that we use to refer to subsets. It's sort of like the squished down, stretched out C with a line under it. And if set A is a subset of set B, we would express that with this symbol. This math equation, or statement here reads A is a subset of B. This would be true if every element in set A is also an element of set B. Okay, some examples here. If we have set A defined as the numbers 1, 3, 5, and 7, and set B is defined as 1, 3, 5, 7, 9, and 11, we could say that set A is a subset of set B because every element in set A is also an element of set B. Okay, when we think about the example of the students that are enrolled in this class, if the students enrolled in this class was defined as the universal set, then one subset would be the students in this class that are currently wearing glasses. Another important set in set theory is the empty set. The empty set can also be called the null set. We have a symbol to represent that empty set. It might be just these brackets with nothing in between them, or sometimes there's a kind of a zero with a line through it. Both symbols represent the empty set. The empty set is simply a set that has no elements in it. All right, a couple of examples of the empty set would be the set of all numbers that are less than 4 and greater than 10. Of course, there are no numbers that satisfy both of those criteria, so this would be equal to the empty set. Another example is in set builder notation, the set of all x such that x is a person taller than 12 feet. Well, I suppose there is a possibility of a person being taller than 12 feet, but I don't know any, so I would say that this is, for me anyway, this is going to be the empty set. You could do it this way, or the brackets with nothing in between them. Okay, we can do operations on sets, just like we do operations in algebra. In algebra, or mathematics, we add, subtract, multiply, divide, take the square root of, raise it to a power, put an exponent on. There's all sorts of operations that we can do on numbers in mathematics. In the study of set theory, which is an arm of mathematics, we can do operations on sets. One operation is to find the complement of a set. To find the complement of a set, we would be looking at all of the elements in the universal set that are not in the set in question. Okay? So if we have a set A, the complement of set A, symbolized by a little apostrophe next to the name of the set, the complement of set A would be all the elements, or all x, such that x is an element of the universal set and x is not an element of set A. There's two new symbols that we're looking at here. This kind of weird, almost looks like a rounded out E. This means is an element of. And then there's also that rounded out E with the line through it. And this means is not an element of. Okay, other system that can be used to define the complement of a set would be that set name with a C up there in the exponent place, or that set name with just a line over it. Let's look at some examples of finding the complement of a set. If the universal set, we'll call it U, is defined as the set of all x such that x is a positive integer less than 12, and set n is defined as 2, 3, 5, 6, 7, and 9, what is n prime, or the complement of n? Right, the complement of n, or n prime, is going to be all the elements that are in this universal set that are not in n. Sometimes it's easier to look at the universal set in its roster method to compare them, so I might write it out that way. In roster method, positive integers less than 12 are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so then if n is 2, 3, 5, 6, 7, and 9, the complement of n is going to be everything that's in U but not in n. Right? So we'll just simply compare the elements. In the universal set, we have a 1, and we do not have it in n. That means it would be in the complement. 2 is in n, 3 is in n, but 4 is in the universal set, but not n. So that would belong in the complement. 5 is in n, 6 is in n, so is 7. 8, however, is in the universal set, but not in n. 9 is in both. 10 and 11 are in the universal set, but not in set n. So the complement of n is going to be 1, 4, 8, 10, and 11. Sometimes we refer to the complement of a set as not n. It's an easier way to remember that, right? In the second example down here, if we have a universal set that's being defined as all the vowels, or A, E, I, O, and U, and S is defined as A, O, and U, what is the complement of S, or S prime? I'll give you a minute to write that down on your own. Did you get E and I? E and I are the complement of S because they're in this universal set, but they're not in the set S. Another operation that we can do on sets is to find the intersection of two sets. When we're finding the intersection of two sets, we're looking for all of the elements that are in both of those sets. The symbol that we use to define the intersection is this kind of funky upside down rounded out U. Okay? And this statement here would read A union B is equal to the set of all x such that x is an element of A and x is an element of B. All right, let's look at an example of finding the union of two sets. If we have set n that's defined as 1, 2, 3, 4, 5, 6, 7, 8, and 9, and set m is defined as 0, 2, 4, 6, 8, and 10, what is n intersected with m? Well, what we're looking for here is all of the elements that are in both sets. So, highlighter here. If I start with set n, I'm looking for anything that's in n and m. Is 1 in m? It is not, so it would not go in the intersection. But look at this. 2 is in both n and m, so it does belong in the intersection. 3 is not in m, but 4 is in both, so that would belong in the intersection. 5 is not in m, 6 is in both, and so is 8. So the intersection of n and m is going to be defined as 2, 4, 6, and 8. What would be the intersection of n with the empty set? Remember, that's one of the symbols for the empty set. We could also look at it this way. In roster symbolism, the empty set is simply the brackets, but nothing in between it, right? So what is going to be intersected with this empty set and set n? Nothing, right? Nothing. There is no intersection there. So it's simply going to be the empty set. All right, another operation we can do on sets is to find the union of two sets. To find the union of two sets, we're going to find all the elements that are in either the first set or the second set. Okay, I always think about the union as like a marriage, right? Two sets get married, and there might be a mother and a father, or a mother and a mother, or two parents at least, and when they're merged together, all the other elements would be the kids, and that would create the new family, right? So we have a symbol to identify the union of sets, It's this weird kind of wide capital U. And the statement here would read, A union B is equal to the set of all x, such that x is an element of A or x is an element of B. Okay, so we're looking for, when we're finding the union, we're looking for all of the elements that are in either one of the sets. It's like we're shoving those two sets together, and we're just going to list all the elements. So with our example of n and m that we were using before, where n is the integers 1 through 9, m is 0, 2, 4, 6, 8, and 10, the union of n and m, it's going to be all of the elements that are in either set. So we want to list everything out. And usually we do list them in order. So the smallest value here would probably be 0, 1. Now 2 is in both sets, but I don't have to list it twice. I only have to list it once when I'm listing the union, because there it is. I don't need to say it again. So we have 3, 4, 5, 6, 7, 8, 9, and 10. The union of sets n and m. What would be the union of set n with the empty set? Well, remember that empty set, it's nothing, right? So when we add that empty set in to n, we're not adding anything to it. So the union of n with the empty set, simply going to be n. 1, 2, 3, 4, 5, 6, 7, 8, and 9. All right, so let's just look at one more example combining some of these set operations in an example. All right, so here we have the universal set that's defined as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. All right, we're looking at all the integers 1 through 11, and we're looking at 0 in there. Okay, there's our union, our universal set. Set n, as before, is defined as 1, 2, 3, 4, 5, 6, 7, 8, 9. Set m, that's our same set that we've been working with, 0, 2, 4, 6, 8, and 10. And we're going to add a third set here, set p, and we're going to define that set as having the elements of 1 and 2 in it. All right, so our first example here says, what is, all right, we have two things going on here, so we have to think about order of operations, right? So what we're looking for here is the complement of the union of sets n and m. All right, so think about that for a minute. We're going to need to find the union of sets m and n first before we can find the complement of that union. Okay, so let's put it up here. Let's find the union. We'll just write it right up here. N union m. Okay, n union m, it's going to be everything that's in either n or m. So that looks like that's going to be 0 through 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so that is the union of n and m. It's the integers 1 through 10 plus 0. So what is the complement of that set? Well, the complement of n union m is going to be everything that's in the universal set that is not in that union. All right, so we'll compare these two sets. We see zeros in both. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 are in both. Looks like the only thing in the universal set that's not in the union of n and m is 11. So the complement of n union m then is going to be 11. Now compare that operation with the next one. The next one is saying something similar but different. It's saying what is the complement of n intersected with the complement of m. Okay, so before I can intersect the complement of n and the complement of m, I need to know what they both are, don't I? Well, let's find them. We'll write them over here. let's just say the complement of n, all right? We want everything that's in the universal set but not in set n. Looks like we've got 0 and 10 and 11. That's all that's in there. Okay, 0, 10, and 11 are the only elements of the universal set that are not in set n. Okay, now let's find the complement of m. Here we want all the elements in the universal set that are not in set m. Okay, so if we look at the universal set, 0 is there, but 1 is not. 2 is in both, 3 is not. 4 is in both, but 5 is not. 6 is in both, 7 is not. 8 is in both, 9 is not. And 10 is in both, but 11 is not. All right, so here is the complement of n and the complement of m. Now that we know what these two complements are, we can intersect them. The intersection of the complement of n and the complement of m is going to be any elements that are in both sets. Well, when we compare these, there's 0 in the complement of n, but not the complement of m. 10 also, not in both. All we have in both is 11. So the complement of n intersected with the complement of m is going to be just 11. It's interesting, isn't it? It's the same as the complement of n union m. The complement of n intersected with the complement of m is the same as the complement of n union m. In fact, that rule will always apply in set theory. This third question is saying, what is m union empty set? Well, we know the empty set is nothing, right? It is a set, but it is a set with no elements in it. Okay, so when we join it or marry it or create a union of that empty set with set m, it doesn't change m at all. 0, 2, 4, 6, 8, and 10 are the elements of m union empty set. This last question here is kind of interesting. This is saying n intersected with m in union with p. Now these parentheses here are forcing an order of operation. These parentheses here are saying, first, I need to find the intersection of n and m. After I find that intersection, then I can join it with p or create a union of that set with p. So first, let's find the intersection. We didn't find that yet, did we? No. Let's find the intersection. We'll just write it here. The intersection of n and m. So n intersected with m, that again is going to be all the elements that are in both sets. Okay? So 0 is not in both, 1 is not in both. It looks like we have 2 in both. 4 is in both. 6 is in both. And 8 is in both. So 2, 4, 6, 8 is going to be the intersection of n and m. Okay, now let's join that with p. So we want to find the union of this set with p. So we're going to add those two sets together. Okay, p's got a 1 in it, so we'll need a 1 here. There's a 2 in both, so we definitely need that 2. Then we'll need the 4, 6, and the 8. Okay, so the union of p with the intersection of n and m is 1, 2, 4, 6, and 8. All right, so far we've been talking about discrete sets, or sets where we can list out all of the elements in roster notation. But in algebra, we often need to deal with continuous sets. Continuous sets are often referred to as intervals, and it's a way of defining inequalities. An interval would be have a lower bound and an upper bound, but it would include all of the values in between there, including any decimal that you can possibly think of. Any decimal that you can possibly think of. So interval notation is very important in algebra, and that's used to define continuous sets. Continuous sets are important because they are the solutions to inequalities. or another way of specifying an inequality. Right? So let's take a look at some of these examples and look at how we would represent these inequalities in different modes. All right, here we have this first inequality says 1 is less than or equal to x, which is less than or equal to 3. All right, I'm a very visual person, so I think I want to graph that first on the number line. All right, so if I stick a number line there, it looks like my smallest number, or my lower bound, is going to be here at 1, and my upper bound would be here at 3. Okay, and the variable x can take on any value in between 1 or 3. So if I wanted to sketch that, let's see if I can find another color. Maybe this red will work. If I wanted to sketch that inequality on the number line, or graph it on the number line, I would want to include all of these values in between 1 and 3, all of them. All of them. Every little decimal that's in there, 1.000001, 2.79358, any value at all that falls in between 1 and 3 should be included in that graph. And when I take a look, the value is between 1 and 3, but look, it says 1 is less than or equal to the value, which is less than or equal to 3. All right? When I have that or equal to situation, I want to include the boundaries of the interval in my representation here. And the way that I do that when I'm graphing it is with a closed-in circle. I would refer to this graph here as a closed interval of values between 1 and 3, because it will include the actual value of 1 and the actual value of 3. All right. To write that in interval notation, I want to say the lower boundary and the upper boundary. So the lower boundary is 1, the upper boundary is 3. I'll separate them by a comma to indicate it's all the values in between as well. But now I want to enclose the lower bound and upper bound with a square bracket like this. The square bracket like this is indicating that I want to include that actual value of 1 in the interval and that actual value of 3, as well as any decimal that falls in between there. So to summarize, if you have less than or equal to, when you graph it, you'll use a closed circle to indicate this is a closed interval. When we write it in interval notation, we use a square bracket next to the upper and lower boundaries to indicate that it is a closed interval, or that we are including this actual value of 1 and this actual value of 3. All right, in set builder notation, that's a little bit more rare, but what we would just do is assign a variable. We know it's x. It's already specified there. We'd say set about x such that 1 is less than or equal to x, which is less than or equal to 3. Okay? Look at this next inequality. -4 is less than x is less than 0. All right, on the number line, we would do much the same thing when we graph this. Our lower boundary here, except would be -4. Our upper boundary here is going to be 0, and we want to indicate all the values in between -4 and 0. So our line would be everything in between there. But this does not say -4 is less than or equal to x. And it does not say x is less than or equal to 0. It just says -4 has to be less than x. This means that we don't include that actual value of -4. The value -3.999999, as many nines as you want to imagine, would be included, but -4 would not. And when we graph that on the number line, we use an open circle to indicate that we do not include the end values. Here we do not include -4 and we do not include 0. This is referred to as an open interval. When we write that in interval notation, we write the lower boundary, use a comma to indicate everything in between. We write the upper boundary, but we don't include that -4, right? It's not less than or equal to, it's just less than. When we graphed it, it was the open circle, so that means we would use a parenthesis a parenthesis next to that boundary. In this case, we also do not include an actual 0. We would use the parenthesis with the 0 as well. Okay, this is referred to as an open interval because it's everything in between there, but not the actual value of the boundary itself. Right? In set builder notation, of course, we would just say the set of all x such that -4 is less than x is less than 0. Okay, this next example, this only has one boundary on it. It says x is greater than 5. Well, when we graph that on the number line, we want to indicate 5. We'll just say 5 is right here. And the values that we're interested in are everything that's greater than 5, right? So it'd be all these values, but it doesn't end. It just keeps going forever. So we want to put an arrow on the end of our line to indicate that it keeps on going. Okay? Now the 5, x is not greater than or equal to 5, it's just greater than 5. So the 5 isn't included here. We want to put an open circle there to show this is an open-ended interval. Well, it's open-ended towards infinity, but also we don't want to include that actual value of 5. Okay? When we write this in interval notation, our lower boundary here is 5. Our upper boundary doesn't exist, so we would use the symbol for infinity to say there is no upper boundary on this interval. Okay? We always use a parenthesis next to infinity because we can never get there, right? It's just a concept. And we've got the open circle. We've got the greater than, not greater than or equal to, so we're going to put a parenthesis by our 5. Okay, in set builder notation, this would be the set of all x such that x is greater than 5. Okay, here we have x is less than or equal to 1 on the number line. This is similar to the one above it, a little different. 1 is our upper boundary in this case, so we'll just say 1 is right there. We want all the values that are less than or equal to 1, so we want to go off to the left to the smaller numbers on the number line, right? There is no lower boundary, so we use an arrow. We use an arrow to indicate there is no lower boundary. That keeps on going forever, right? And here, in this case, the value for x, it could be equal to 1, so we want to use a closed circle on the 1 to indicate we can include that actual value, right? In interval notation, our upper boundary is 1. Our lower boundary, there isn't 1, so we use negative infinity to indicate that our interval goes forever in the negative direction. Of course, negative infinity is also a value we can never reach, so we stick a parenthesis by that. Here, the 1 can be included because x is less than or equal to 1, so we want to use a square bracket by the 1. And then in set builder notation, we would just say the set of all x such that x is less than or equal to 1. Okay. This next example has 2 inequalities in one statement. Our value here can either be less than 1 or it could be greater than or equal to 5. Well, let's see. Let's graph that on the number line. All right, we're going to need we'll say 1 is here for this example and 5 is here. So our values here can either be less than 1, so we've got to go off in the negative direction, but there's no lower boundary, so we'll put an arrow by that. No lower boundary. And it can't be equal to 1, so that's open, so we'll put a circle there by the 1. And then we can also have values that are greater than or equal to 5. So greater than 5, we'll draw here with an arrow to indicate it goes forever. And it can be equal to 5, so we need to close this end of the interval or use the closed circle. All right, when we write that in interval notation, we'll look at this. There are 2 intervals on the number line. So we're going to need to indicate 2 intervals here in interval notation. The first interval is going to be negative infinity to 1. Right, 1 is my upper boundary. There's no lower boundary. I always have a parenthesis by infinity and negative infinity. The 1 has to be excluded. It's not less than or equal to, and it's got the open circle. So that'll be a parenthesis there. Our second interval is going to be everything greater than 5. My lower boundary is 5. I don't have an upper boundary, so that would be infinity. I always have a parenthesis by infinity. Here we can include our 5. It's greater than or equal to the closed circle. So I'm going to put a square bracket there. And I have to do one more thing. And when I'm referring to sets, even continuous sets like this in interval notation, I need to use this union symbol in here to show that the values I'm interested in here are the union of the continuous set from negative infinity to 1, excluding the 1, and the continuous set from 5 to infinity, including the 5. Right? Or I might say the open interval from negative infinity to 1 in union with the closed interval from 5 to infinity. Okay, then of course set builder notation is just a set of all x, such that x is less than 1 or x is greater than or equal to 5. Okay, look at this third example here. There's a lot going on in this one, right? We still have two situations, two inequalities. The first inequality is a compound inequality. It's just saying that x has to be in between 2 and 3, inclusive of 3. And then the second inequality says x could also be greater than 10. So I'm visual. Many of you are going to be visual like me. I always like to graph it first so I can see what this looks like on the number line. So when I graph that, let's see, I've got some boundaries, 2, 3, and 10. We'll say 2 is there, 3 is there, and 10 is over here. All right, the first interval is everything between 2 and 3. It's open interval next to 2. It's a closed interval by 3, right? So everything between 2 and 3, all right, there you go, all those values there. Not including that 2, it's open at 2, so open circle. It's closed at 3 because we could include that actual value of 3, so close it there. And then my second part here is everything greater than 10, okay? So an arrow, not including that 10 though, we don't have the line under it, we don't have the or equal to, so that would be an open circle. In interval notation, I have two intervals to specify here again. My first one is between 2 and 3, so I'll say 2, 3. We're open on the lower end next to the 2, that's a parenthesis. We're closed with the 3, that's a bracket. Okay. My second interval is everything greater than 10. Okay. So that would be 10 to infinity, always open by infinity. The 10 is not or equal to, it's not greater than or equal to 10, so I need a parenthesis. It's open next to the 10. Of course, I have two sets here, two continuous sets, right, or two intervals, so I'll need to stick that union symbol in there to show that I'm interested in all of these values. I'm interested in the values of the first set in union with the values of the second set. My set builder notation, set of all x, such that 2 is less than x is less than or equal to 3, or x is greater than 10. Okay, this last example is kind of interesting, all real numbers. How do we indicate all real numbers on the number line? Well, it's just everything, right? It's just everything. So I guess we would just repeat the entire number line like that. And my sloppy line, sorry about that. There we go. Everything. What about the interval notation? There's no lower bound, there's no upper bound, right? So that's simply going to be negative infinity to positive infinity. And we need parentheses, of course, so we never reach either negative or positive infinity. In set builder notation, we're just going to say the set of all x such that x is a real number. Okay, so various examples of interpreting inequalities into interval notation. Inequalities are simple continuous sets. They're sets that have an infinite number of elements in them. They include all the decimal values in between the boundaries, and sometimes they include the boundary itself if we have an or equal to under them. I always recommend, if you struggle with this a little bit, to graph your inequalities first before you write your interval notation. All right, let's look at a few examples before we wrap this up. First example says, graph the set P, which is defined as a set of all x such that x is less than 2 or x is greater than or equal to 7. And then write it in interval notation. All right, so if we're going to graph it, let's put a number line on here. We've got a few boundaries there. They're indicated, 2 and 7. So we'll just say 2 is here and 7 is over here. Now my values, well, there's two inequalities going on here. My first one is everything less than 2, and that's an open interval. So we use the open circle with an arrow off to the left, to the negative direction on the number line to show everything less than 2. But the value we're interested in could also be greater than or equal to 7. So that's going to be a closed interval at 7, goes in that circle, but open on the positive end. It goes forever, right? So there's the graph. Excuse me. In interval notation, we've got 2 lines, so we have 2 sets, right? We have 2 continuous sets. The first set, negative infinity to 2, but open at 2, in union with the second set, closed at 7, that's a square bracket, and going on forever to positive infinity. Look at the second example here. Graph the set S that's defined as the set of all x such that x is greater than negative 3 and x is less than or equal to 2. Then write it in interval notation. I'll give you a minute, or maybe you want to pause the video and see if you can do that one on your own. Here's my graph. I want values for x that are greater than negative 3, but open at negative 3. It's not or equal to. And also the values need to be less than or equal to 2. Okay? So even though there's 2 inequalities, it ends up being just one interval. All these values between negative 3 and 2 closed by the 2. In interval notation, that's going to be negative 3 to 2. With a bracket by the 2 to indicate that the interval is closed at that end. Okay. What if we want to find the union of 2 intervals? What if we want to find the union of 2 intervals, right? Well, what we're really just doing is kind of what we're looking at over here. There's 2 intervals. There's the union. Sometimes intervals may overlap, though, as well. Let's look at these 2 continuous sets, find the union, and then we'll go ahead and graph it. And I think might do it in reverse order. I think visual. I think I'll graph it first, and then I'll specify it in interval notation. All right, let's see what that looks like on the number line. Let's see. I'm going to need a negative. I've got several boundaries here, right? Look, I've got a negative 2. We'll say that's there. I'm going to need a 3. We'll say that's there. 6 and an 11. 6 might be there. 11 might be there. Something like that. Okay. So set A, I said that's red, right? Set A is everything between negative 2 and 6. We're closed at 6. Solid circle there. We're open at negative 2. Open circle there. And then our second set B, let's see if I have another color. Orange, that looks a lot like red. What else can I find in here? How about green? Oh, that'll show up better. Our second set B, so if A is our red set, we're going to say We're going to say B is our green set. Our second set, B, is everything between 3 and 11. Okay, so I'll just sketch that up above it. Everything between 3 and 11. Okay, it's going to be closed at 11, but open at 3. Okay, so I need to find the union of these two sets, A, union B. Well, the union is going to be everything that's in either set, right? The easiest way to write the union of A and B when I've got them graphed is indicate everything where there's at least one line, right? So my absolute smallest number here is -2, but it's open at -2. So I'll use the parenthesis by the -2. And I keep going all the way until I get to 11. There's some overlap here between 3 and 6. That's fine. But there's at least one line there. There's no breaks. There might have been a break here at 3 if I didn't have the value of 3 covered in set A, because it doesn't include it. It's not included in set B. But I don't have to worry about that because we're finding a union here, right? So it has to be in either set, right? So my highest value then is going to be 11, and that's closed by the 11, so I'll put a bracket next to that. Let me ask you a question. Is this the same one? Nah. The next slide is the same thing. Let's just write it right on here. What is the intersection of sets A and B? What is the intersection of the two sets? Well, the intersection of the two sets is all of the elements that are in both sets. So from the number line, the intersection of those two sets is going to be everywhere that we have 2 lines where they overlap. So the intersection of A and B is going to be everything between 3 and 6. Oops, wrong color. I'm getting too many colors involved here. Okay, 3 and 6, everything between 3 and 6. At the 3, of course, it's open because there's an open circle there. But wait a minute. Yeah, it's got to be in both. Yep, so we want to open next to the 3. At the 6, it's closed, so we can put a bracket by the 6. Parenthesis by the 3 because it's open. The 3 is not included in set B. Bracket by the 6 because it's closed, because 6 is included in set A and in set B. All right. Let's see. Let's look at one more example. Let's see if we can find the intersection of 2 sets, right? 2 continuous sets, or the intersection of these intervals. The word disjoint is sticking out over here. What does that mean? I'm going to leave you hanging on that for a minute. Let's see. Let's graph it first. I want to graph first. Let's look at the graph first. All right, so let's see. What do we have here? We have just 6 and 11 are the only boundaries. Let's put a 6 there and 11 there. Okay, our first set, -infinity to 6, closed at the 6. So we need this closed circle at the 6. Everything less than -6 out to -infinity. So that arrow is going to say that goes on there forever. Okay, then B is everything greater than 11, but it's open at the 11. So I'll put an open circle there. It's out there. All right, so now we're looking for the intersection of those two sets. Remember, the intersection, that occurred where there was overlap, right? It's all the values that are in both sets. Well, there's no overlap here at all, is there? There's none. So the intersection then has to be the empty set. It has to be the empty set. You can use either symbol, it really wouldn't matter. What about the union of these two sets? The next thing is saying, oh, that's a different one. What about the union? Let's do it. Let's just find the union for the heck of it. A union B. Okay, that's everything that's in either A or B, right? Either set. So let's see, that's just going to be -infinity to 6, closed at the 6, in union with 11 to infinity, open at the 11. Let's just do one more example. the intersection of two sets. Go ahead and pause the video if you want to try this one on your own. So there's my graph. The red one is set A, the green one is set B. Where do they intersect? They intersect everywhere that there's two lines, right? Where the elements are in both sets. So let's see, it looks like we have to start at -2, but we have to exclude that -2. So let's open it at -2. And we can go all the way to 6. We have both lines, right? Or the elements are in both sets up till 6, closed at 6. Because of course 6 is in set B and in set A. Between 6 and 12, we only have set B occurring, right? All those elements between 6 and 12 are not included in A, so they can't be in the intersection, right? But there's overlap again. We have overlap from here to here. That's our union, is overlap, right? And we also have overlap from here to here. So A intersected B. First overlap is between -2 and 6. The second overlap is between 12 and 23. And it looks like it's open at both ends there. And we have two sets, so we need to indicate the union symbol to show that the intersection of A and B occurs between -2 and 6, this first continuous set, in union with between 12 and 23, this continuous set. All right, that ends the lecture on sets.